this is the fun one. In fact, if we start getting back in our labs, this is a lab that we are going to be doing. This is the stinky lab that is so famous here at Riverdale High School. All right. Now, this is the last of the carbonyl groups. This is the last of the oxyorganics. We're going to do amines next, which is nitrogen-based, not oxygen-based. And we're going to take a slightly different approach to how we're talking about this. First of all, we are going to get into the definition like we always do. And so this is going to be, like I said, a carbonyl group. So we're going to have RC double bond O. And then the difference here is, and you're just going to love this. We've had OH here for the carboxylic acids. And so we're going to go back to that, but instead of having a hydrogen on there, we are going to put another alkyl group on there. So guess what that looks like? And ether. Okay. But it's not going to take on the necessary complexity that we had with the oxy attachments on the IUPAC name for esters, or ethers rather. We're done with that. But this is what we have here, and we write this as RCOO R prime, where R prime may or may not be the same length as the original R. It's just another alkyl group, whatever it is. Now, again, I want to also mention here that this R and this R prime, this R here can be a hydrogen, just like it was for the aldehyde and the carboxylic acid. Kind of is okay to consider it that way because it fits the definitions for the rest. Those are the only two functional groups that do that. That's the acids and the aldehydes. For the ester, because of that, we can also use that as an H as well because it involves an acid, as you're about to find out. Now, so let's talk about the physical properties for this. Take a close look at this structure right here. We have oxygens here and here, but we don't have a hydrogen bond to either one of those two oxygens. But this is polar. In fact, it's got 2 points of polarity on it. So that certainly helps. So this is considered polar, which means that you can have, it can be dissolved in water up to, and I'm going to say slightly more than 6 carbons, but I'll leave it at 6 carbons because who really cares anyway. But it can be soluble higher than that. But I haven't really looked at the data that closely. And because of the fact that there's no hydrogen bond to the oxygens, the intermolecular bonding then is going to be dipole-dipole. And because of the fact that it's dipole-dipole, it means it's going to have a medium boiling point and freezing point, and it's going to have a medium vapor pressure. And that kind of dovetails into a use that we have for it. Now, we talk about uses here. This is really, 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 really big in flavorings. A lot of the smells, these, shall we say, synthetic smells that we use for candies and gums and all that, are usually esters. So we'll just put flavoring down as a very generic way of saying that's what we use it for. And like I said, the lab that we're going to do, we're going to be making these synthetic odors. Fruity smells. Lots of fruity smells. Mint smells, a lot of mint smells. Foot odor is actually an ester. In fact, I'm not sure we have the stuff to make foot odor. We used to make it, and oh man, it would just make people gag. And of course, the Chem 2 students just love that because they have some sort of power over the rest of the student body that nobody else has at that point. So we will be dealing with that. And because of that, we are going to be looking at the reactions of making these right now. Now we put, with the exception of the alcohols, we put all the reactions off to a couple lessons from now when we get into the reactions of oxyorganic compounds. We're not going to do that with this. We're going to do it right now because it helps us get into the nomenclature. So our next section is nomenclature and reactions. And when I say reactions, I'm talking about synthetic reactions. How in the world do we make these things? And it's from those reactions that allow us to figure out what the names for these things are. Otherwise, it could be a bit challenging, but if you follow the reaction on these things, this is going to help a lot. Now, how do we make an ester? So we're going to look at the synthesis of esters, and we're going to do it from a very generic point of view. In order for that to happen, you have to take carboxylic acid plus alcohol, but they won't react on their own. The amount of activation energy is a bit too much for room temperature conditions, and we'll talk about that later on as well. So we need a little chemical kick in the butt that we call a catalyst. And we talked about catalysts way back when. And so this is what's going to happen here. We're going to add a catalyst. Usually it's about as strong an acid as you can find that is not ridiculous. There's some silicon fluoride acids out there that we want no part of. But the strongest of the available acids is sulfuric acid. And that's generally what we're going to be using as a catalyst. And since it is technically part of the reaction, but in the bookkeeping aspect it's not, we put it above the arrow and say, yeah, it's there, but it kind of isn't. And this will produce an ester, and a byproduct is water. And it turns out esters, like we said, are very soluble in water, for the most part, because of those two oxygens in the compound. So if I show this from a linear structure point of view, an acid is RCOOH. Now we haven't talked a lot about acids, and last year we didn't. We had some dealings with acids, but I don't know how much you remember from last year. I kind of have an idea how much. But according to Arrhenius, and to a certain extent Brunson-Lowry, this hydrogen, which is technically a proton, comes off. And so that is the acid part of oxyacids. It's the hydrogen part of the oxyacids. Plus alcohol. So we use R'OH for that. And I'm just distinguishing the length of the carbon chain from the length of this carbon chain here. They may be the same, they may not be, it's not important, but we identify them as R'. Now, OH. Now again, I don't know how much you remember from last year, I'm guessing not too much, but we had acids and bases reacting together in what we call a neutralization reaction. They neutralize each other. Acids and bases are exactly opposites. And so, now, the problem is that most of the bases we talked about last year were rather easily removable. Alcohols, OHs are not that much, and that's why we need a catalyst to get this thing going. And just to give you a very quick overview, one of the hydrogen ions off of the acid gets attracted to this oxygen right here and creates an H2O positive ion. which very easily comes off. Now we can remove it because water is very stable, and it makes this positive here as a result, and that gets attracted to where this is right here. This comes off rather easy when it's dissolved in water. It's not a strong acid, but it's enough of a strong acid where it will happen fairly easily, and then R prime will replace the H. So it's kind of a double displacement reaction at the same time as being an acid-base reaction, which is technically a double displacement reaction. So, and I'll put H positive here because we're just looking at a proton off of that, or a hydrogen ion off of that sulfuric acid as our catalyst. We don't have to write the whole thing out, but you want to show off to your friends, you go right ahead. But the H is going to be removed, and the OH is going to be removed, and that's where your water is coming from. And the R prime, like I said, is going to come over here and replace the H there, and the H here is going to come over and replace the R prime here, double displacement reaction, and we get RCOOR prime plus H2O. That's your ester. But because this is just like an acid-base reaction, and acid-base reactions that we dealt with last year, mostly, but not always, mostly dealt with ionic compounds. And when you react two compounds to create an ionic and a negative ion, a positive ion and a negative ion together, we call those salts. That was a salt. Any ionic compound is called a salt. We call this an organic salt because it's coming from an acid-base reaction with some technical differences. So an ester is an organic salt that's dissolved in water. All right, so let's look at some examples here, shall we?